Hello folks, and welcome to this first lecture of MATH7019, Applied Technological Maths. So just in this lecture we're just going to try and give you a flavour of what this module is all about. Okay. I suppose before we start we might want to say something like this module is compulsory for your third year studies, and there's a module in the second semester which is an option. I'm sure your coordinators will talk to you. I suppose it's not an option, it's elective. If you want to go into level 8 structural engineering, you're going to want to take this second elective module. What I've tried to do in this module is take all the stuff that's possibly useful now and put it in one module. So the second module is a bit more abstract because it's kind of background maths for structural engineering, whereas this is, if this is the last maths you do, there's stuff in this that's designed to be possibly useful to you in your career. Okay. So the kind of things that we're looking at, so we're going to do some curve fitting, which is essentially mathematical modeling. This is our first chapter. Then we're going to look at beam equations. Now this really is just the maths behind some of the one of the structural analysis modules next semester. Then we're going to do some probability and statistics. Now it's going to mostly be focused on statistics, mostly you understanding sampling theory and hypothesis testing. Now in the background behind statistics is probability, but it's not going to be a big focus for us. And the last thing is Taylor series, which is basically in engineering mathematics, a lot of the time you can't solve problems exactly. So what you're forced to do is make approximations, and this is all about that. In terms of assessment, I don't want to be too prescriptive at the moment because I haven't decided everything, but my expectation is that we're going to have 4 assignments: an assignment on this, an assignment on this, an assignment on this, and an assignment on this. In a normal year where there'd be 30% continuous assessment and a 70% exam, 30% of the continuous assessment is a chapter 1 assignment and a chapter 2 assignment. So I've already got those. I just need to think about these two. Okay. So some information here. This manual, by the way, I'll probably write this in an email, but there's probably 3 ways that you can do this. You can just follow the lectures. Now I don't think that's a good idea because we're going to be writing in these manuals, and I think in maths it's important to be writing. But in theory, you could actually just watch the lectures and not do any writing if you wanted. In theory, you could. The second thing to do would be probably once every week or so, all the lectures that I do, I'm going to scan the notes. So you could use those to be additional notes. The third thing you could do would be to kind of use the scanned notes and write some of the notes yourself. The fourth thing you can do is you could print off all these notes. So I'm going to send this PDF and actually write as you watch the lectures. That's probably what I would advise. Well, actually what I really advise is to actually get this printed and bound and get it as a single manual. Now normally this would be done in the copy center. I've emailed them once or twice. They haven't quite gotten back to me, so we'll see about that. So website, email. Actually, my email, I shouldn't use this Gmail account anymore. Mostly, of course, we're going to be using Canvas, in fact. So basically, I'm just going to say Canvas is how you contact me. There is some stuff on the website, the jpmccarthymaths.com, older stuff in this category, MATH7019, but to be quite honest with you, there's nothing really useful there in terms of everything that's been seen before. I'm just actually repeating kind of similar stuff, so you're going to get all that again. This is just saying what the module is about. We don't have to get into the content too much. Here's the assessment. So this is not decided yet, but I'm looking at maybe 4 25% assessments, or 2 30% and 2 20%, or 2 30% and 1 40%. I'm not really sure. In general, in other years, I insist on that assessments be on time, and I just ask for what you give me, whatever you have done on the day you hand up. I'll probably go with the same again, but obviously we're going to have to be a bit more how we say, accommodating, considering the situation we're in. I'm not going to be out to get you. This is just about making things easy, because you're going to have a lot of assessment, and if you're going late on assessment, they're all going to build up and you're going to produce lots of poor work. I think just basically submit things on time or early. Exercises. So like one way that's not really going to work for you is just say watching the videos. That's really not going to work. What you're going to have to do, like at a minimum even, is to be writing what I'm writing. But really what you want to do possibly is watch the lectures, but you have to listen, you have to do exercises. So my recommendation would probably, I will probably be recommending, considering that, you know, we don't have the commuting and everything, that you spend at least 7 hours a week on MATH7019. That is my recommendation. So that's probably of the order of 2 or 3 hours watching lectures and 4 hours doing exercises. This is my strong recommendation, either doing exercises or doing continuous assessment. I'm going to set up assignments on Canvas so that you can submit work every week, and I'll correct the work you hand in weekly, and also I will answer emails essentially 7 days a week. Okay. Yeah, so this is kind of explaining that you really must do exercise. This is how you're going to learn. I suppose you don't have exams, but if you're facing into an assessment having done no exercises, you're going to really be lost. So the exercises are going to kind of build you up with enough understanding to be able to do the assessments. Like as an analogy, the exercises are something like a soccer player using a rowing machine. It'll build up some kind of aerobic fitness that'll help them doing what they actually want to do, and you can kind of think of the exercise as being a similar story here. In terms of reading this manual, these notes are going to be pretty much comprehensive, but there are some things here that might be available as ebooks in the library, I'm not sure. Okay, so just to give you a flavor of what we're going to do in this module, let's look at some learning outcomes. So these are things that in theory you'll be able to do afterwards. So the first is find and use the curve of best fit. So the idea would be, okay, let's see some data on the next page. So here we got some data. So these typically come from a measurement. Now usually the X is something that we control. So like this could even be, I don't know, maybe these are properties of a beam. This could be the length of the beam. So you control the length of the beam. Now this 0 obviously doesn't make sense there. So maybe this is 50 centimeters, 1 meter, 1.5, 2, 2.5, 3, 3.5, 4. You get the idea. So you produce the beam of that length. You put a particular load on it, and maybe Y is the maximum deflection, something like that. Now the idea is that whenever you make a measurement, there's going to be errors. Now to make this kind of consistent, have to be fairly big errors, but so this is what you measure, say the maximum deflection to be, but there's going to be errors. Now those errors have lots of different sources, but they're in there. So the idea is that the data that you have always has errors. Lots of different ways that can happen. But what you want to do is somehow underneath all this with the errors, just the kind of the true values. So you think of the measurements as the true value plus an error. And your job in curve fitting is to find essentially the true values. So this curve is supposed to represent the true values. And so say if this is whatever x equal to 8, that you've got the true value plus the error gives you the measurement. And the idea is that the errors should be uncorrelated. So like this one has a positive error, but the ones down here is a negative error. And the idea is that the more and more data or measurements you have, those errors should kind of even out, and somehow you end up with something that is the true behavior. We will be learning how to, given these data, so these will all be given in terms of data points. Say, for example, whatever this is, say 8 for argument's sake, let's say 0.17. You'll be given all these data points, and our job is to come up with a formula for this curve, which is called the curve of best fit. Okay, that's what chapter 1 is going to be all about. Chapter 2, we're going to want to understand what a differential equation is. So for example here, we'll probably see the solution on the next page. This is actually, this differential equation governs the bending moment of a beam with a point load of 18 kilonewtons 1 meter along the beam, and it's a simply supported beam. So the idea here is that a differential equation, you understand that the solution, you're looking for m of x is what you're looking for. So you're looking for a function that has this property. When you differentiate it twice, you get minus 18 times. We'll learn about this delta bit later on. And what you can think of a function essentially is kind of a graph. It's giving the bending moment in terms of the distance along the beam. And if you pick different distances, calculate the bending moment and then plot all of those, you're going to get a curve. So to understand that the solution of a differential equation is a function which you can essentially think about like a graph or a curve. So here you see the bending moment as a function of distance along the beam. So to understand that and also actually solve these static beam equations, the static, I'm not sure, the beam isn't going to be moving and the load isn't going to be moving. I think if you went to level 8, you're going to have both of those things happening. The beam actually vibrating or maybe a load moving. So what we're going to have is, these are the differential equations we're going to look at. We're going to find, given this is a load per unit length, given a loading on a beam, find the bending moment and find the deflection. Okay, so these are going to be things that we do in chapter 2. In chapter 3, and actually at the end of chapter 2, we're going to use Taylor series to approximate solutions of differential equations. There's 2 scenarios when differential equations you can't solve them. One is that, so to solve this one, what you can do is you can anti-differentiate both sides. A lot of the differential equations we see are going to be like that, just simply anti-differentiate both sides. But there are things you can't anti-differentiate. So for example, if I want to find the antiderivative of e to the minus x squared, there is such a function, but you can't write it down in terms of things you know about. This is called, it doesn't have an elementary, the language is, it doesn't have an elementary antiderivative. So the question is, yeah, that's grand, but I still want to actually, say, solve the differential equation. So one of the things you can do is do some kind of an approximation. There's loads of different ways. We'll see this in the thing, because what you're going to learn is, while all the maths you've been doing up to this point, you've been getting exact solutions. In the real world, really, you don't. You need approximation. So this is one of the scenarios. A more realistic scenario that, again, we'll talk about is where, say you've got a load, you're looking at a beam and you've got a bespoke load. So this is, some kind of weird loading on the beam, and you don't have a formula for it. Now, chapter 1, by the way, the curve fitting might be able to give you a formula for it, but in general, you mightn't have a formula, you might just have data. So the question is, how do you solve the differential equation when the w of x is given in terms of data? That's another time you'll need approximate solutions, and we're going to use something called Taylor series to do that. And the last thing we're going to do is we're going to use the normal distribution to solve engineering problems. So the normal distribution essentially is just the bell-shaped curve, and there's kind of different ways that we can use all that statistics theory to do things. So here, if you want to find the average strength of a component using a structure, you take a random sample and estimate. How good is that approximation? Like, say if you take steel rods and you measure the strength of 10 of them. Well, how accurate is that? Like, say you measure the strength of 10 of them, you take the average and you say, oh, this is the story, but how accurate is it? Something else, suppose someone claims that a component's quality is disimproved over the past year. How can you test that claim? We'll answer this, and we'll see different examples. So there's one actually off the top of my head. There's an old bridge up by Cove somewhere, and they wanted to test the strength of the concrete, and what they obviously, you can't take down the bridge to test the concrete, so they just took a sample, they bored some holes. So the question is, how accurate is this as a technique? This is what we'll be studying in, that'll actually be chapter 3.